Hi everyone, my name is Matthias and I'm from University of Zurich. I'm very glad to talk to you today, so thanks very much for inviting me. Today's topic is exploring an alternative to beam search that is based on sampling in NMT. I should maybe add, since I'm not claiming to cover the entirety of NLP that uses beam search, so maybe in NMT should have gone in the title as well. Here's a short overview of the talk. So it's divided into 4 short sections. We'll start by introducing some well-known shortcomings of NMT that are old news, I would say. Then we'll discuss the role of beam search in causing these problems or making them worse. And then we'll get to the meat of the talk, which is investigating if an alternative to beam search called MBR causes fewer problems. And then I'll finish off with some unsolved problems and potential future work in this direction. Right, let's dive into the first part, which is well-known shortcomings of NMT. And this is redundant right now, but I figured it would come in handy later to remember where we are in the talk. Right, now, unfortunately, NMT suffers from a plethora of different shortcomings, many more than I can list or introduce in this talk, and most of them also wouldn't be relevant to the experiments. So the ones that I chose to introduce and that are relevant to the experiments also are length bias, the low robustness to noise in the training data, and the low domain robustness. And I'm quickly going to talk about each of these now. Starting with length bias. What length bias means is simply that overall NMT systems have a tendency to produce translations that are shorter than reference translations. So in other words, NMT length bias means that translations are too short. And as a quick example, I have a table with results from our recent experiments where length is measured as the average number of tokens of sentences in a translated test set. And you can see that on average, the reference translations are 11.9 tokens long, and translations produced with beam search with a beam size of 5 on average are 11.6 tokens long. Now, a difference of 0.3 tokens on average might seem small to you, and you would be right. But also, I think the more important finding is that this behavior of translations being too short is consistent across many language pairs and also many data conditions. And here I wanted to mention that in the bottom right corner, for your convenience, I'm always mentioning where I'm taking certain figures or numbers from. And also, if relevant, I'm giving you the language pair that the results are about, because that's information that I would love to see in a talk like that, and that's why I'm including it. Right, now let's move on to the second shortcoming that I'll introduce, which is low robustness to copy noise. And to give you the gist first, NMT systems in general are sensitive to certain kinds of noises in the training data. So this shortcoming is about the training data, and one type of noise that is the most detrimental to have in your training data is copy noise of the following kind. So here is an example. Imagine we are translating from Arabic to German, and this is an instance of the kind of noise I mean, where the source and the target are identical and both are in the source language in Arabic. So that was a pretty long explanation for something pretty simple. So this kind of source copy noise is really, while it is simple to remove, also to detect in your training data and to remove, it's also extremely devastating for translation quality, and it has a disproportionate effect as well. And I will explain in a second why I think that the effect or the impact of this is disproportionate. First, let me show you the general impact that source copy noise has with numbers from our recent experiments. So what this graph is showing is translation quality measured with blue on the y-axis, and the x-axis are different NMT systems trained on training data where different fractions of all the examples are source copies. So we're starting on the left with 0.1% of all training examples being source copies, and then and this end is on this end it's 50% of all examples are source copies. And overall, this has a very detrimental effect on translation quality, as you might have guessed. So, for instance, if 10% of all training examples are source copies, this reduces the blue score from above 20 to below 10, just eyeballing from this graph. Now, why am I saying that the impact is disproportionate? I have a different graph which shows this much better. Here the x-axis is the same, and the y-axis is in a translated test set. What's the percentage of all sentences that are copies of their inputs? And from this graph you can see much better that let's again take this column where 10% of all training examples are copies. You can see that a training set like this results in 50% of all sentences in a test set being copies of their inputs. And that's why I'm claiming that the effect of source copy noise is disproportionate, or clearly copies are overrepresented in beam search. Right, and then moving on to the last shortcoming, which is low domain robustness. Again, to give you the gist first, domain robustness is about out-of-domain translation, which means the following. It means to train an empty system on one domain of text and test it on different domains that it hasn't seen during training. For instance, train it on a medical text and then test it on other domains like law text, IT, Quran, and subtitle text. And while this has an obvious impact on translation quality, so obviously the translation quality as measured by blue, for instance, in these domains is not great, but it also has more more intriguing effects, such as hallucination. Hallucination basically means that a system in out-of-domain translation or under domain shift, empty systems have a tendency to produce translations that are fluent but not adequate at all. And here's an example to illustrate this from our own experiments last year, where the input sentence is in German, aber geh subtil dabei vor, and the reference translation is but be subtle about it. But what the system produces as a translation is pharmacokinetic parameters and so on. I'm not going to read the entire sentence, but clearly it's a sentence that is completely fluent. It's a fluent text, very reminiscent of medical text, but also it doesn't have, it's not related to the input in any way, and that's what makes it a hallucination. And now an important message takeaway message here is that under domain shift or in out of domain translation, hallucination is a much more pronounced phenomenon. And here I have a graph which shows this a bit better. So remember that that medical text is the training domain, and the other domains are just ones that the system is tested on. So testing on the other domains is what out of domain translation means. And the y-axis in this graph is, in a translated test set, how many sentences are hallucinations. And as you can see, the exact percentage of hallucinations in translations, it depends heavily on the domain, maybe on the distance between domains. Maybe that's one possible explanation for this. But in some domains, hallucination is quite common. For instance, if you train a system on medical text and you evaluate it on IT text, then more than 25% of all sentences in a test set are hallucinations. Right, so that's it for this part. As a quick summary, NMT has some well-known and well-documented failure cases, and examples that I introduced are length bias, sensitivity to copy noise, and low domain robustness. And something I completely forgot to mention is, as I hinted at in the beginning, all of these shortcomings are old news. And we are, or I am by no means the first person to notice these behaviors or report them, not by a long shot. I just chose to illustrate with numbers and figures from my own experiments, but I wouldn't want to take the credit for discovering or reporting these issues first.